Hey everyone, this is Mr. Hausman. We're looking at one of the more challenging problems that we will be practicing in our problem set. Thank you for the students who brought this to my attention. I'm not sure if there's a problems with the answer key, but we're going to break this problem down into a few smaller steps rather than looking at all the answers at once. So let's begin. So let's start with what we always call the inside-outside approach to finding our total. Right, so let me put away a few tools. And we always start with resistance, right? We're trying to find the total resistance of the circuit. So I see a battery, and we color code things to kind of keep things easy to see. And it's got a high voltage side, right? So there's got to be 18 volts here, 18 volts here, right? You go anywhere from the positive end of the battery, the long line, and you show, right, that there's 18 volts going in here. Now, where is it 0 volts? Well, if you work backwards from the negative terminal, it's 0 volts through there, and you actually stop right there. The 6 ohm resistor, right, has to have some voltage left over at the end. Let's do a little reminder. We've got 18 volts to 16 volts. Okay, now we said we were solving for resistance, so let's begin. Inside to outside. Well, I see that these two are clearly connected in parallel. They're parallel to each other. Now you say they don't connect at a node over here. Well, you can kind of say, right, that this is the node on the right and this is the node on the left. There's a split here and it comes back together there, and there's no other pathway. So when you add 42 and 21 in parallel, you simply get 14. So let's write a little note to ourselves that that's a 14 ohm equivalent resistance there. Then, if you look out a little bit wider, and we've done this before, where we kind of do these groupings, and we say, oh, these two are series to each other, so now we've got 4 plus 14. Let me pause for a minute and kind of show some of my work. So there we have the first resistors in our circuit. 14 in parallel, and then 14 plus 4 in series. Well, we got to do one more step further down to keep adding that. And what you'll notice is that this junction here, this node where the circuit splits, it's actually a common node for where it comes back after the top resistor. So you'll notice that this path and this path, right, this whole bottom part, they're parallel to each other. So 9 to the negative 1 plus the 18 that we just found in the middle pathway to the negative 1. And we have to add those and also take that to the negative first power. And that's a parallel pathway. And I see that that comes out to be a 6 ohm resistor. And a lot of people are asking me, wait a minute, isn't the 6 on the bottom also parallel? And it very much looks parallel because of math terminology. It's a pathway that's flat and doesn't cross the other two. But really what's happening is that there is a 6 at the very end. And I want to show you a trick I showed some people. If you want to think of it this way, does it help some people? You could move this resistor, the 6 ohm resistor, you could move it out here. You could put another resistor out here, or really a different resistor, and then make it come back over here. That, to a lot of people, makes more sense, but it's really the same thing. And of course, you'd have to break this wire, right? That wire wouldn't be there. It would come back here to this junction, and then it would go out through the 6 and then back through the battery. So I'm going to leave both, but really, that's the same resistor. So I guess the take-home message then is that R of the entire top path is 6 ohms, plus R of that very bottom path, right? So this is just simple series, R1 plus R2 equals R series. So 6 plus 6, or a total resistance of 12 ohms. So finally, we put that in, 12 ohms for the whole circuit. And then current is not the hardest part. I is equal to V over R. And we've got an 18 volt battery, 18 over 12. And many of us see that that's got 6s in it, so it's 3 over 2, or 1.5 amperes. Okay, pretty challenging start, and it does get more complicated from there. Well, I see, again, a pretty complicated circuit, but we've seen circuits in the past where, I'm going to see if I can use the pointer tool, where sometimes there's this one resistor out here that's after all of this, and this is the complicated parallel, series, parallel part, and then this 6 out here is kind of like, it's not an afterthought, it's the last one in the line. And frequently, what you can do is as soon as you now know that the current is 1.5 amps, you can put that in where you know that to be true. And a couple places it would be true would be right here, 1.5 amps. That's the total current. And it's a very short little path. But isn't it also 1.5 here? And again, on this side, 1.5 amps. So this 6 ohm resistor, this one down here, this guy is guaranteed to have 1.5 amps flowing through it. Okay, so let's put that in, 1.5 amps. And then by simple Ohm's law, V equals IR, 6 times 1.5, or 9 volts. And, we should be pretty, comfortable with that. V equals IR, and it came out to be 9 volts. But this is where a lot of people get stuck. And I say, what do you do with that 9 volts? Well, you show that you know where that is and what it means. And it means that this guy, that 6 ohm resistor, just lost 9 volts. So that means 9 volts has to be saved. Well, let me see if I can grab another tool color here, a little pen color, and make it orange. No, let's make it green, and here's what I mean. So we know that, right, and the next warmer color up from blue is green. And what we have basically said is that if it's 0 volts here, right, it's 9 volts, remaining all the way through. That 9 volts goes up here. We're going to go back to the original circuit and things like that. And 9 volts here and here and here and here. So this is 9 volts. And so we put that in 0 to 9 and the 9 volts. And you start to notice, you're like, wait a minute, I think I start to get it. The 9 ohm resistor at the top is going from 18 to 9. And that must mean 18 to 9 is a loss of, right, another 9. And so the second resistor I would do, after doing the 6 in the bottom, I'd actually go to the 9 in the top. And it must be 9 volts. I is V over R, so 9 over 9, 1 amp. When you know that you've got 1 amp, you put it in the circuit where you just said it was, 1 amp. That means through the 9 ohm resistor. Okay, now, weirdly, we're going to jump from working backwards to working forwards, and let me show you what I mean. We knew that going into this junction, there had been a total of 1.5 amps. And if 1 amp goes through this top path, and then it merges back and it's 1.5 here, but really just remember, 1 amp across the top, what's 1.5 minus this 1 amp? And what you start to realize is that must mean that there's 0.5 amps left on the bottom pathway or the middle path. There's 1 up here and then 1.5 and then 1.5 total. So you get 1.5 amps there. So I think, oops, get that out of the way. There's a 0.5 amp current flowing through the 4. V equals IR. The product of those two is 2 volts. And again, I don't delay. This is not a rush. But as soon as I calculate a number, I put it in here, 2 volts. And once I know that that was a drop of 2 volts, remember, the red represents 18 volts, so 18 minus 2 must be 16 volts. And I think I have to use, one more color. Let's see if I can do this in a little yellow. And this yellow color here, right, also goes down here, right? It's going from, let's see, 18 minus 2, so that's 16 volts. And it's dropping off to, and it has to come out 9 volts. 16 minus 9 is you need to drop off 5 volts. And who has to get it? The 42 and the 21. So 5 volts, 5 volts. They both get it because they're in parallel. And I equals V over R 5 over 42. Let's see if I did that right. 5 divided by 42, or basically 0.12 amps, and then 5 over 21. Not a whole number, 0.23. And let's see if those add up. I'm very sorry, I just caught a mistake. It's not so easy to do a full edit and explain everything. We'll just do a quick cleanup. It's really basic math. It's not good that I mixed that up. But essentially, I took 16 volts. Let's find where that was. It was just a minute ago when I assigned the voltage to this last part. 16 volts minus 9 is not 5, right? Because 5 plus 9 is only 14. This is actually 7 volts. So my fault. Some of you probably saw that a while ago and were wondering if I was going to catch it. 7 volts. Let's do a little cleaning up here. And there we go. Pop those out. Let's recalculate those pretty quickly. And we get I equals V over R. 7 divided by 42 is 0.17 amperes. And 7 divided by 21 is 0.3. And that may not look like it adds up to a total current of 0.5. I'm referring to these two together adding up to 0.5. But remember, it's 0.3 repeating, and 0.17 had more decimal points after it. So when you add it up in your calculator, you're going to get 0.499666, or it's going to be really close. So I think that's a pretty complete, detailed approach to this problem.